In this lecture, we will continue to discuss the adverse effect of nonlinearity of an amplifier. We had already discussed what will be the consequence of nonlinearity on the frequency content of the output for single tone input. Today, first we will discuss what will be the consequence on the amplitude of the output for single tone input. We will see that it leads to a phenomena called gain compression. And then we will take up the case of two-tone input, and there we will see the effect on frequency content and the amplitude. And there we will see that there will be few additional unwanted frequency component present at the output, and they will be called as intermodulation, and they are more difficult to handle. So it will be pointed out why they are more challenging. So first we will talk about gain compression. Here gain compression, simple word, means reduction of gain. So this phenomena occurs when we have nonlinearity in an amplifier. So now let us take an amplifier which is being fed with input voltage Vi, and we have output voltage Vo. Now, since this is non-linear and we are considering non-linearity only up to third order, so this output we know that will be given by this expression. Where our input is a single sinusoid like this. So we had already carried out the output analysis. That means we can substitute this input in equation 1 and find out what will be the output for the fundamental case. So if you find out the output for the above input, the fundamental, which we will designate as VO1, and this is a non-linear case, so we will call it VO1N. So this will turn out to be A1A. This is what ideally we should get, but then there will be a component arising because of the cubic term. Recall that second order term is not going to contribute any fundamental frequency at the output. So here is the contribution coming from this term, ideal term, and this contribution is coming from the cubic term. And for ideal case, what we should get is this thing. And it was also pointed out that usually the coefficients are for higher power, they are small. That means say A3 is going to be small. So this was pointed out. And now let me add another important point, that usually A1 and A3, they will be of opposite sign. So here we have this scenario, and now you can see that the overall amplitude of the fundamental has two components, from the ideal and from the third order, and they are of opposite sign. That means as the amplitude of the input, this amplitude capital A grows, the amplitude of the fundamental for nonlinear case is going to reduce slowly and slowly. So it is basically this property of the fundamental for this nonlinear case which leads to phenomena of gain reduction or gain compression. So we will try to characterize this nonlinear amplifier for the gain reduction, and then we will try to find out what is that input for which the output power is less than the input power by 1 dB. So this phenomena is characterized by a parameter called 1 dB gain compression point, and by definition it means the output power, say in dBm, for ideal case minus the output power also in dBm for nonlinear case is equal to 1 dB. So the input for which this uh, point is observed is called 1 dB gain compression point. So now we will try to find out what is this point. So first we will have to find out the power associated with the fundamental for ideal case, and then for the non-ideal case, and then implement this equation 2. So So we have already pointed out, so this is equation 1a, this is 1b. So this output power for the ideal case will be equal to A1A square by 2R. And this is going to be in watts. So here we assume that this power is being delivered to a load of value R. And we know that in RF and microwave, all the loads are going to be of the same value. Now we have written this equation 2 in dBm, but this could be in dB also. So let us write this power in dBm. So what we will have to do is, first we will have to convert this into milliwatt, so that this will become 10 raised power 3 A1 A whole square by 2R milliwatt. So now we can convert it into dBm. So PO ideal in dBm is going to be 10 log of the power. So this is dBm. Now here we will write this expression as a function of input power. So input power Ti is going to be A square by 2R, because input is A cos omega t. So this is in watts. So Pi in dBm is going to be 10 log 10 raised power 3 A square by 2R dBm. So from this equation 3, we will separate out the input power term. So equation 3 can be rewritten as 10 log 10 raised power 3 a squared by 2r, and will separate out a1 square term. So what we see is that output power is equal to the input power in dBm plus a constant term. This term is constant for a given amplifier. So what we have here is a straight line equation, y is equal to x plus c1, and here slope is 1. So it was pointed out that as the amplitude of the input increases, the amplitude of the fundamental for nonlinear will reduce because of this cubic term, because of this term. So first we want to know what will be the growth of the fundamental with respect to input for ideal case. So this is how the ideal output power will vary with the input. So now if you make a plot of this equation 4, so this is with respect to input power in dBm. So here what we see is we have a straight line with slope is equal to 1. So the slope of this line is 1, and it passes from C1 on y-axis, which has output power also in dBm. So this is the ideal response. This is how we should get the output power for ideal amplifier. But now let us try to find out the output power for non-ideal amplifier, and then plot that output power also on this same curve. And then we will impose the definition of 1 dB gain compression point to find out the input amplitude corresponding to 1 dB gain compression. So first we will have to find out the output power for this non-ideal case. So we had already found out the amplitude. So the output power for nonlinear case is going to be amplitude square divided by 2r. So amplitude was found out as a1a plus 3 by 4 a3 a cube. So this was the amplitude. So it's square divided by 2r. So this much watt of power will be contributed by the fundamental with third order nonlinearity of the amplifier. Now we have to convert this into dBm. So first we will convert this into milliwatt. So this becomes 10 raised power 3 a1a plus 3 by 4 a3 cube divided by 2r milliwatt. And then in dBm, this becomes 10 log 10 raised to power 3 A1A plus 3 by 4 A3 A cube whole square divided by 2R. So this is dBm. Recall that we could have arrived this equation by dividing this output power by 1 milliwatt, which is the alternate definition for dBm. That means dBm is power normalized to 1 milliwatt in logarithmic scale. But both will give rise to same answer. So here what we find is that this above expression will have the effect of this cubic term very small if capital A, that means the input itself is very small. So this will approximate to 10 log n raised to power 3 A1A whole square divided by 2R dBm for very small a, because a is raised to power 3. So if a is small, its value will be smaller compared with this, because a3 is already very small. It was pointed out. So what we see now here is that we have expression, this expression, which is similar to that of the ideal case. So this is similar to ideal case. That means equal to output power for ideal case, and this happens for very small a. That means when a is small, there will be overlap between the growth of the power for the both the cases. So here we again have PON dBm equal to 10 log 10 raised to power 3 A1 A square by 2R. Now if you want to write this in terms of input, so we will get the same expression what we got earlier. Here. So what we are getting is x plus C1, same constant. So this is for the nonlinear case. So for small a, the plot will be similar to this one. There will be no distinction. But as the a increases, this, when a becomes sufficiently large, this term will start growing faster than this. And then on the whole, this value will become smaller than this case, ideal case, or that means small a case. So what will happen is now the output power will become smaller than this small input case. That means the output will now start reducing like this. So this is a non-linear. This is PO non-linear, and earlier one was or ideal case. So here you can see that there will be point, there will be input such that this difference in the output power for the two cases will be equal to 1 dB. Keep in mind that both the powers are in dBm, so their difference is going to be 1 dB. This we have already discussed in the previous class. So now we are going to find out what will be this value. So for this case, we have to find out the ideal minus the actual case. So this is the ideal case. both in dBm. Here also there is a mistake. This should be like this. This is A1 square. Now here we will write the actual expression for non-ideal case, not the approximated one. So this will become minus 10 log. We can divide this second argument with this one. So now if you solve this for the input A, so input A square will turn out to be 0.145 A1 by A3. So the input amplitude for which 1 dB gain compression occurs is designated as A1 AdB equal to 0.145 square root A1 by A3. So this is the input amplitude, and the corresponding input power is given by P1 dB equal to 10 log so this is going to be dBm. So we need to know this 1 dB gain compression point for an amplifier so that we always try to keep our input below this point. And this phenomena of the gain compression is undesired, especially if the input signal is amplitude modulated, because in that case, so here you can see that what this graph says, that if my input is within this region, say if it is in this region, well below the gain compression point, then what happens is that every frequency component will get amplified by same amount. However, if the amplitude comes closer to this region, the 1 dB point, then the larger amplitude portion of the input signal will get amplified by less amount compared with the smaller one. So there will be distortion in the output for amplitude modulated signal. However, for frequency modulated signal where the amplitude always remains constant, this 1 dB gain compression point has no adverse effect on the output. So the masses doesn't get distort for the frequency modulated signal, but amplitude modulated signal might get affected if the peak amplitude of the signal falls in this region. So this was one way of finding out 1 dB gain compression point. There is another way in which gain compression point can be found out. So the equation that we wrote, or the defining equation for 1 dB gain compression point, was this: ideal case minus non-ideal case is equal to 1 dB. Now recall that at this moment, both the amplifiers, the ideal amplifier and the non-ideal amplifier, they are in theory being fed by the same input. So same input is being fed for both ideal amplifier and the non-ideal amplifier. So what we can do now is we can subtract the input for the ideal case and subtract the input for non-ideal case, and we still have the same equation. So keep in mind that all these powers, they are in dBm. So here what we have is output minus input power for ideal case. That means this becomes gain for ideal amplifier, and this is output minus input for non-ideal amplifier. That means this becomes the gain for non-ideal amplifier. All these powers are in dBm. So another equation that can be used to define or to find out the 1 dB gain compression point is this equation. That means ideal gain in dB minus non-ideal gain in dB equal to 1 dB. So this will also give rise to same input power. So this was the undesired effect for one tone input on the amplitude of the output. Now we are going to study the undesired effects on the output when we have two tone inputs. So we have this amplifier which is nonlinear, and we are interested in the adverse effect on the frequency component and the amplitude of the output. But this time, now the input has two frequency components. So in this case, our input is, and to keep the thing simple, we will take the amplitude of both the sinusoids equal. So this is the kind of input that is now being fed to nonlinear amplifier, and output, we know that, is going to be given by this expression. So we will see that in this case, we will get certain other type of frequency component on the output side, and they are called intermodulation products. Output components. And then we will try to characterize the amplifier for certain value of input for which this intermodulation product lead to unwanted phenomena. So to find out what will be the output, we have to substitute this input, say from equation 5 into equation 6. and then carry out the complete analysis. And in this case, because we have two sinusoids, so finding out square and cube will involve a lot of terms. So we will not write the exact expression for the final output. Rather, we will take each term one by one. And it is easy to see that the first order term will have no effect. It will simply multiply each of the two sinusoids by uh, small a, which is the usual gain of the amplifier. So for output for the first term, that means A1 VI. So output frequency component will be are going to be located at omega 1 and omega 2. That means we will continue to get cos omega 1t, cos omega 2t, and these are the desired ones. Now let us see what happens for the second term. Output for the second term, that means A2 VI square. So what will be the role of this? So we know that this will basically involve expanding this term here. So here we have, say, x and this is y. So we know that what we are going to get for x plus y square is x square plus y square plus 2xy. So x square term means we are going to get a square cos square omega 1t. And this type of term we have already encountered for one tone case, and we found that this gives rise to two components, one at DC and second at 2 omega 1. Similarly, the second term cos square omega 2t, this will also give rise to two terms, again at DC and at 2 omega 2. That means the second harmonic. So we are already familiar with this for the one tone case. Now we are going to get a new term. So XY type of term is going to give rise to cos omega 1t, cos omega 2t. And this, when we carry out the expansion, will give rise to two cosine terms, cos omega 2 minus omega 1t and cos omega 2 plus omega 1t. So these two terms will arise. So here we see that there are going to be again two frequency components, but which we never encounter for one tone case. One will be located here, omega 2 minus omega 1. Second is going to be located at omega 2 plus omega 1. So these types of term where we have a sinusoid arising because of the mixing of the two tones are called intermodulation products. So these are intermodulation products. And specifically, these two frequency component, they are the consequence of the second order term. So they are called second order intermodulation products. Now let us see that what happens because of the cubic term. So we are now going to talk about the output due to the third term. That means A3Vi cube. What it will do. So Vi is sum of two cosines. So Vi is A cos omega 1t plus cos omega 2t, right? So this whole thing is like x and this is going to be like y. So this cubic term will actually do this thing, and we know that this will give rise to four terms: x cube, y cube, 3x square y plus 3xy square. So we will now have to find out contribution of each of these four terms and how this will give rise to various frequency components present on the output side. So now when we carry out the effect of cubic term, so this will involve expanding cos cube omega t. This type of term we have already handled for the one tone case. And when we expand this, what we are going to get is by 4, 3 cos omega 1t plus 3, sorry, cos 3 omega 1t. So here what we see is we have a fundamental and we have third harmonic, omega 1 and 3 omega 1. So this cubic term gives rise to fundamentals of the fundamental and the third harmonic. Similarly, for the omega 2t, we will get two terms. Now, what about this second, third, and fourth term, where both cos omega 1 and cos omega 2 will be involved? So, for x square y type of term, what we are going to get is cos omega 1t whole square into cos omega 2t. So if we carry out expansion of this, what we will get is 1 by 2 cos omega 2t, the fundamental, plus 1 by 4 cos 2 omega 1 minus omega 2t plus cos 2 omega 1 plus omega 2t. So this is what we will get from the mixed term. So here we are getting the usual fundamental term, but now we are getting frequency components which involve both the input frequency components, and these are also called intermodulation products. But these two frequency components, they have come into existence because of the cubic term. So these are called third intermodulation products. So in this case, what we see is this is going to give rise to fundamental and two intermodulation products. Now let us see that this term is difference of two frequency components. So this one will be approximately equal to omega 1 in it will be located closer to omega 1. But this one will be located almost 3 times of the omega 1, assuming that omega 1 and omega 2, they are very close to each other. In fact, this one is going to be smaller than omega 1, right? Similarly, xy square, this is going to give rise to omega 1 and 2 omega 2 minus omega 1 and 2 omega 2 plus omega 1. Now this one is going to be closer to omega 2. In fact, this one will be larger than omega 2, right? So now we have all the frequency components, and let us plot them on frequency axis to see that where each of the components are going to be located, and then try to figure out which of them will be more difficult to handle. So this is frequency axis, and here we are going to get our usual fundamentals. But we will see that these fundamental amplitudes are not going to be uh, equal to that of the ideal case. They will have contribution coming from the third order terms. So here we have omega 1 and omega 2. So now if you talk about this cubic term, then what we see is we have this fundamental. So that is why I said that these amplitudes, they are not that of the ideal case. They will have contribution coming from the cubic terms. And then we have this term, as was pointed out, this one will be closer to omega 1, but smaller than. So this will be on the left side, while this one is closer to omega 2, but larger than omega 2. So it will be on the right hand side. And these two components, other mixed component, they are going to be very large. So let us first plot them. So we are going to have, this is 2 omega 1 minus omega 2, and then there will be here 2 omega 2 minus omega 1. And then we will have 2 omega 1 plus omega 2 and 2 omega 2 plus omega 1. So these are the components from the mix, but from the pure component like this x cube term, we see that we have fundamental again and third harmonics. So we will again have a fundamental which will add with the original one. So what we have shown here is resultant of all of them. Now we are going to have a third harmonic 3 omega 1 and 3 omega 2. So these are the contribution, 6 terms arising because of the cubic term. Now let us see that what is the contribution of the second order term. So for the second order, we have already seen there will be DC, second harmonic, and then omega 2 minus omega 1, omega 2 plus omega 1. So this one will be closer to DC, and this one will be closer to 2 times omega 1 or omega 2. So now we can plot the contribution of the second order term. So we have already seen this will give rise to component at 2 omega 1 and 2 omega 2. And then there will be term at omega 1 plus omega 2, which will be in between 2 omega 1 and 2 omega 2. And then there will be DC term, of course, and then there will be a term close to DC, which will be, say, omega 1 minus omega 2. Actually, let us say that this is omega 2 minus omega 1. So these are the frequency component that we will see for two-tone input. So here what we see is that most of the components, they are widely separated, like this one, and this one. They all are quite away from the desired one. This is desired one. So one can always put a filter with certain characteristic centered around the desired. So we can have a band pass filter with this center frequency, and this will filter out these components. But we find that filtering out these two intermodulation products, they are going to be a lot more difficult. So they are going to create a problem. So this is the disadvantage of third order intermodulation product, which does not happen for the second order term. Now we are going to find out a parameter that is called input third intercept point. In short, IP3. So this is I, this is 3, IP. So we are now going to estimate this term for the amplifier. So here, before we do this, we would like to note down the amplitude of the fundamental for non-ideal case and for the ideal case. So this amplitude for the non-ideal case is going to be A1A, arising because of the first term of the nonlinearity, and 9/4. If you carry out the detailed expansion of the expression and collect all the fundamental terms, this is what we will get. So, and here one can see that this is going to be approximately equal to A1A for small a. That means when the input amplitude is small, the fundamental amplitude for nonlinear case is similar to that of the ideal case or linear case. Only when amplitude becomes large, it starts getting deviated. So here we found that these intermodulation products, they are very problematic because they are going to be very close to the desired ones. These are the desired ones. And their amplitude is going to be 3/4 A3 A cube. So this is third IM products. Now here you can see that when the amplitude of the input increases, this will increase very fast because it has third power of the input, capital A cube. So in the beginning for small, this will have very small value, and what you will see here is a very small component compared with the ideal one. But as the input amplitude increases, they will increase very fast because they have cubic power. And here A1 and A3, they are of opposite sign. So they will start getting compressed, and there will be scenario when this will possibly catch up with the ideal one. These two, they will become equal. So then now we try to find out what is that input for which they will become equal if their small input plots are extended. So here, let me first try to find out power for these two cases, and then we will try to equate them to find out what will be the input for which they will tend to intersect each other. That means the third order intermodulation product will become comparable or equal to that of the fundamental. Fundamental for this ideal case, not for this actual case. So let us first try to find out power for each of these two cases. So for small input, keep in mind that we are doing this thing for small input. So this is going to be power for the fundamental for small input. Now, if we want to find out it in dBm, and here we will separate it out, or we will write this expression in terms of input power. So 10 log 10 raised power 3 a cube by 2r plus 10 log a1 square. So here this is input power in dBm. So plus 10 log a1 square. This is constant. So we again have equation like y is equal to x plus c1, where this is c1. Now for the third intermodulation product, so this is in watt. Now when we convert this into milliwatt, this becomes 3 by 4 a3 a cube whole square by 2r milliwatt. Now our objective will be to write this also as function of the input power. That means this quantity. So we will do some manipulation here. So we multiply and divide by 10 raised power 6. So this becomes 9. And we have to convert this also into cube. So we multiply and divide by 2r squared. This. So this is now milliwatt. And here we have to write in terms of input power. So we then separate out capital A terms. So this is still in milliwatt. Now we will convert it into dBm by taking 10 log. So here we will rearrange these terms. So 10 raised power 3 a square 2r cube. And this term we will write separately. Like this. So here this becomes 3 into 10 log 10 raised power 3 a square by 2r plus this constant. So what we now have is 3 into P in dBm plus C3 PO3N. So this gives rise to equation y is equal to 3x plus C3. So what we see is that the third order intermodulation product amplitude uh, gives rise to a straight line with slope is equal to 3. That means it grows very fast compared with the fundamental amplitude for small input or the ideal case. So if we make the plot of these two on same graph, then what we have here is we have our usual or the fundamental, and keep in mind this is only for small a, and what we got now for the third intermodulation product is a straight line like this with slope is equal to 3. So this is third IM. So here we can see that if we were to extend these two plots, they will intersect at a point. And this point actually does not occur in real life because this plot, keep in mind, is for small a. That means for the ideal case. For the actual case, we know that cubic term also contributes to the fundamental and it starts reducing the amplitude. So this intersect point is obtained by plotting these two curves for small a and then extrapolating them. So that input for which they will supposedly intersect each other is called IIP3. Input third intercept point. So this is another parameter which is used to characterize an amplifier. Now we would like to estimate what will be this input point. So as you can see, this is the point where the amplitude of the fundamental for small a, or for ideal case, is equal to the amplitude or the power for the third intermodulation product. So here we have already found out the power for the fundamental or the small amplitude case is going to be this thing. And power for third intermodulation product is going to be this thing. So this IP3 is the point where these two powers, they are equal. So we are equating this thing in the linear absolute scale, but this equality will remain valid in log scale also. So here we get A1 A by 2R whole square is equal to 3 by 4 A3 A cube whole square 1 by 2R. So when we simplify, what we get is A1A. We are taking mod because A1 and A3, they are going to be of opposite sign. So here A, this will cancel out. And if we solve, A will turn out to be 4 by 3 mod A1 by A3. So this is the amplitude of the input for which third intermodulation product power will become equal to that of the ideal case for the fundamental, or the small amplitude for the fundamental when it is extended. Right, so corresponding input power for IIP3 in dBm can be found out as 10 log 10 raised to power 3 AIP3 square by 2R. P1 dB and AIP3 or P in IP3, they are the two important parameters which are used to characterize the nonlinear behavior of an RF amplifier.